Okay, so 2.6 is our last section in this unit, and it's called integration by substitution. So far, you know how to integrate basic derivatives. You know how to do the power rule, you know sine, cosine. That's really all you know. So think back to when you took derivatives. We did the same thing. You learned basic derivatives, and then I taught you the product rule, the quotient rule, the chain rule, okay? And like implicit differentiation. So this is kind of our first way to approach that. We don't necessarily have those same type of rules for integrals as we do with derivatives. So what this is doing today is basically the quote-unquote chain rule. It's actually the backwards chain rule for integration. Products and quotients are much more difficult, and that's more of a Calculus 2 topic, something that you see in the second semester. That's what we're going to do in the spring, okay? But substitution is typically in a Calc 1, so we cover Calc 1 and 2 in this class. All right, so substitution. So first of all, like I said, it's kind of like undoing of the chain rule. So it's good to go back. So remember, an integration is just an antiderivative. So let's look at the derivative. If I'm taking the derivative of a composition of functions, so chain rule, what is that rule? F
prime of g of x times g prime of x.
Correct. Okay, so what I'm looking at is if I want to integrate something that looks like f prime of g of x times g prime of x, then that would end up being f of g of x, okay? That's basically what I'm doing. This is a lot harder than taking the derivative of a composition. Because what you have to do when you're looking for an integral, you have to see what this g prime piece is. You have to you have to train your eye to see you have this inside function, and then you have a factor, see it's being multiplied. You have a factor that is the derivative of your inside functions. Okay, so that's what you're going to be looking for. All right, so I'm going to go through the steps of how to undo the chain rule, which is basically taking the integral of a composition function. And what we're going to be using to help us with this is using U substitution. I think you did this with Ms. Vorwerk, U substitution. U substitution just basically means replacing an entire function with just the letter U, and it's a placeholder not for a variable but for a function. And it allows you to do easier math with that function, and then you substitute that function back in. You did that a lot with quadratic formula and things like that to make the quadratic formula easier for you. We're doing that same thing with integration, okay? So what your U, so you're gonna have to choose the appropriate U. This sometimes is a little bit of guess and check. Even when I look at new problems, sometimes have to guess and check. And I might start with one U, and then that's wrong, and I might have to start with a different U. So it takes some practice getting to see what the U is. Some are very easy, but typically you don't get the easy ones. All right? So the first thing you're going to do is identify an inner function. See, my inner function is what's going to be kind of inside another function. It's the composition, right? So that g of x, in this example, is the U. Okay, so that's what you're looking for. That's your U. And you want to identify an inner function U whose derivative is also a factor of the integrand. And so you can see if U is g of x, then the derivative of U is g prime. Does that make sense? Right? If the derivative of U would be g prime if U is g. Okay. All right, so that's what we're going to do. Then, so once you find U, you calculate the derivative of that inner function, and then you do substitutions, antiderivative, differentiate, and then back substitute. I'm going to show you all those steps. They make more sense when we actually do it. Okay, so let me do it in generic terms, and then we'll do it with an actual problem. So again, if I've got this, let me just show you the process of how to get to the final answer. All right, so we would find the inner function is g of u. So u is going to be not g of u, g of x. Oh my goodness gracious. I wish it didn't do that every time. Oh my gosh. G of x. And so then du dx. So you have something in terms of u, like if it was y equals g of x, we would write dy dx. Since it's u, we write du dx because we're taking the derivative with respect to x, okay? So this is in terms of x, so that makes sense. So du dx is equal to g prime of x, yes? Okay? And then what you do is you actually, just like we've done before, I'm going to move this dx piece, kind of like multiplication in quotations. I'm going to move this dx piece over here with this g prime. So I'll show you why we do that in just a second, but I'm going to move that dx over with the g prime. Okay, now the reason I do that is this whole thing is called substitution. So this whole thing, everything is in terms of x. I want to substitute everything, and I want to see something in terms of only u. All right, so I have the integral of f prime. That didn't change, nothing changed there. Of g of x. Well, we call g of x what? U. So now that's our first, so f prime of u times, and now you see this g prime of x piece times dx. That whole thing becomes du. You see that substitution? So it's all about trying to manipulate, okay, your derivatives around so that you can make those clear substitutions. It's going to look a little different based on the problem that you have. So now that whole piece becomes du. Okay, and so now everything's in terms of du, because if you change f prime in terms of u, but you still have a dx, it doesn't work. To integrate, they have to be of the same variable. Does that make sense? It has to be all in terms of u in order to take the integral now. And now, do you know this? What's the integral? Okay, so this is kind of like, Kate, when you're talking about the difference between t and x. That's just a dummy variable, okay? I can interchange that. Okay, what's the integral of f prime of x dx? F of x. And so that just goes straight to that. What's the integral of f prime of u du? F of u. Yeah. Always a fun one, yeah? Yes?
Can you have an integral without...
You got it now? Yeah. What?
Can you have an integral without the, like, endpoints?
You mean the d?
No, like, you know how you say you take the
Yeah,
integral?
this would be an indefinite integral, what we first learned. This is an indefinite.
With, like, the rectangles?
Right.
With the rectangles, that kind of thing?
So an indefinite integral is, it's going to be a function of x. So you take the antiderivative, it's just in general.
Oh.
And then remember the plus c, remember it's like a family of functions. So like what has a derivative of 2x? X squared. X squared was 1, x squared was 2, x squared was 3. Does that make sense?
Yeah.
Okay. All right. So y'all see this now? And then, so what we did is we anti-differentiated with respect to u. So we have to have everything in terms of u to do that. And now we're going to back substitute because we want it back in terms of x. So now all we do is replace the u with what u is. And that was g of x. Okay? And that's the general process. That's the general process. We just back substituted. We just replaced u back in terms of x.
This is only like indefinite integration question mark?
Yes. Now, you can do it with definite integration as well, and we're going to look at that. But right now, we're just looking at definite integration. Yeah. Okay? So indefinite integration does not have limits of integration. What your answer is a function of x. Definite integration, you get a numerical value that represents the area under the curve.
You have the B and A, right?
Say it one more time.
You have the B and then the A.
Yeah, that's the A and the B. Yeah.
What's the indefinite integral function?
The antiderivative function. So if I have a function of 2x, then what's the antiderivative? What function has a derivative of 2x? X squared. So it's represented by the function.
So it doesn't represent anything to do with the area.
It still does. It's like if I know, I can still apply that with a definite integral. Like each point can represent the change in accumulation. Okay. All right. So example 1. Now let's actually try this. So example 1 is quite easy. You typically don't get them this easy. All right. And the reason why it's easy is because if you look at the inner function, right, you see 7x squared plus 3, and then you easily see the derivative of that function is 14x. It's kind of a low ball, all right? They're kind of handing it to you, and normally that doesn't actually happen. But we're going to start off with that one, to help us kind of see the process. Okay, so going through our steps, we need to identify, you need to choose a U function. Okay, so it gets more complicated as far as what to choose as U, but typically, rule of thumb is you're looking for an inside function. Okay, so you want to look for an outer function with a different function inside. That's clear to me that that's 7x squared plus 3. Yes? So that is my entire U. That whole thing is U, 7x squared plus 3. It's kind of like the peanut. You're looking for the peanut. Okay. Then you take du with respect to x. So du is going to be equal to 14x. Now, you could do it like this. This is technically the step that you would take, du dx equals 14x. I normally skip that and just go ahead and know that I'm going to throw my dx on the end. You must include the dx. That's super important because it comes into play when you're substituting. Okay, so now, this one's right nice and easy because they hand it to us. Du is 14x dx. So that whole piece gets replaced when I substitute with du. And so now I have the integral of u to the 8th du. So now that's a much easier integral. Okay, that's just power rule. What's the integral of u to the 8th with respect to u? 1/9 u to the 9th plus c. So we took the antiderivative, and now we back substitute. So now we just replace our u with in terms of x. And that's our answer. Okay? I hope you are still saying that to me.
Yeah, it's about
That was a low baller. You'll probably never see one like that again. Okay? All right. Example 2 is much more like what you would see. It's not that much more difficult, but there's a little twist. Just a little. Okay? Same exact concept, same exact process. Let me show you now why it's different. Okay, just looking at this, what do you think u is? X squared. It's your inner function. The x would not be because that's on the outside, so you would want the peanut, the x squared. Okay, so that's our u. So then du is 2x dx. So here's the little twist. This is much more like what you would see. And so notice that if I rewrite this, let me rewrite.
There's still an x.
Correct, there's still an x, which that's the important piece. If I rewrite this with the x, I'm going to put a little dot to kind of show that. Okay, if I rewrite this to put the x on this side, because I've got that x dx, okay, but the 2 is a little bit of a problem, but that's okay because it's a constant multiple. As long as it is a constant multiple. So let's understand what a constant multiple is. A constant is not a variable, okay, and it's multiplying, not adding. Division is actually an extension of multiplication because dividing by 2 is the same as multiplying by a half. So division is okay. It's adding and subtracting that's not okay. Everybody good with that? A constant multiple. So since that 2 is a constant multiple, that's okay. It does not pose a big problem. It's all about substitution. I know now when I substitute, you're going to have the integral of cosine of u, right? But now I need to take care of that x dx. I need x dx. So all you have to do is get x dx by itself. Right, you just divide by 2. So does everyone agree if I divide by 2, then x dx is equal to 1/2 du. Everybody agree with that statement? So now I'm looking for what x dx is. X dx is 1/2 du. So when I substitute, the 1/2 is okay. Now, if that was a variable, that would not be okay. But a constant multiple, totally okay. I can throw that into my problem. Does that make sense? Yes.
Would you end up taking the 1/2 like out of the integral?
Yes, exactly. That would be my next step. So is everyone okay with my substitutions? Yes.
So when I looked at it, I was like, oh, the outer function could just be 1/2 cosine. Is that, can you like approach it that way?
You
too?
could approach it that way. Yes.
Okay.
You'd still have the 1/2.
Yeah.
Yeah. Mm-hmm. So, and then just like Kate just said, anytime I have a constant multiple, I pull that out. So then that 1/2 can move anywhere around in that statement. So I'm going to pull that 1/2 out, and now I'm just taking the integral of cosine. And what's the integral of cosine? Sine. So we just get 1/2 sine of u plus c, back substitute, and we get 1/2 sine of, I think it was x squared, plus c. Questions? That's more typical. Okay, so in that first one, you typically won't see that 14 there. They don't just hand you the derivative.
That's unfortunate.
Okay, so now let's look at the next one. So now we have the integral of sine times cosine. So when we've got trig in there, it's a little bit trickier. When you've got trig in there, remember your u, you want to choose u. There's clearly not really a inside function here, okay, but you can still do this by u substitution. Because sine and cosine are basically derivatives of each other, right? Does that make sense? They're basically derivatives of each other, right? Derivative of sine is cosine, derivative of cosine is negative sine, okay? So your u actually can be either sine or cosine in this one, okay? So we're going to do both ways. So let's try the first way. The way that makes sense to me is the one that you don't get negative, right? So u, it would be sine, so that your du would be the positive cosine, right? Okay, so the first way, we're going to let u be sine. Du is cosine x dx. Don't forget that dx piece. Does everyone remember why the dx is there? Because technically it's du dx, right? Then we bring the dx over. Okay? All right, so now we're going to substitute. So now we have the integral. Sine of x becomes u. Cosine x dx, that whole piece, is du. And now that's a super easy integral. What is that?
1/2 squared.
Oh, that's 1/2 u squared plus c. Yes? And now back substitute.
Wait. Oh.
You didn't even have to solve for du for this one.
Say one more time.
Oh yeah, you did. Never mind.
Okay.
Can you solve it a different way?
Yeah.
If you do the double.
That's the third way, actually. Yeah. Okay, so the second way is calling u cosine. So I just want to show you what we end up getting. So if u is cosine, we would end up du being negative sine x dx. And so when I'm looking at my integral, I've got sine x and I've got dx. I just need to multiply by a negative. Does that make sense? If you want to get sine x dx by itself, and you can write it like this. So the whole sine x dx piece, that and that, what I've circled, combined, will be replaced with negative du. Everybody with me? And then I'm just going to go ahead and pull that negative out in front. So let me see if y'all are okay with this. So this is going to be a negative integral of u du. Is that okay? So sine x dx, what I've circled,
Oh, okay, I'm following.
that whole thing gets replaced with negative du. Cosine x gets replaced with u. And then I pull the negative out. Everybody good with that?
Yeah.
Okay. Then integrating, we get that same thing, but this time it's going to be negative 1/2 u squared plus c, which is negative 1/2 cosine squared x plus c. Now, both of these integrals are correct. They don't look the same, though. Are they the same? Is 1/2 sine squared plus c equal to negative 1/2 cosine squared plus c? Yes, as long as the c's are not the same. Here's why. Because, and I'll show you, because, remember Big Daddy? Sine squared plus cosine squared equals 1. So sine squared, and you can multiply by any constant, right? Sine squared equals 1 minus cosine squared x, or we could rewrite that as negative cosine squared x plus 1. So if you just drop the 1/2, because it's not a big deal. So sine squared is equal to negative cosine squared plus a constant. So these are the same, but their c values would not necessarily
They have
be
to
the
be
same.
different by one.
They would have to be different by 1. Correct. Yeah. Okay. Yes, sir. Or yes, no.
Okay, so
I was looking at him when I said the pronoun. Yes.
So the negative out in front of the integral, would you not, this is probably a stupid question, I think I know what you're gonna say, but would you not need to distribute it to the c? Like, I know it's a constant, so it doesn't matter, but
Correct.
like.
It's just okay. So you just have to transcend your thinking. So this c is not necessarily the same c that you would get before you distribute. It doesn't matter. It doesn't matter. Yeah. Okay. All right. Good. Okay. All right. Now we get to example 4. Did you say there's a third way?
Is there a third way?
There is a third way. What do you think it is? I know Chase knows what it is. Gabe, what
I
it
have
is?
no idea.
Okay. There's this old formula. You do not actually. The AP test is not.
Sine of 2 theta.
Remember that, Jewel, from last year?
Yeah. Oh my god. And then
The
you do
AP
it.
test.
Oh.
The AP test does not make you memorize those. The only ones in the AP test you have to know are the Big Daddy and the ones that come from that one. Those are the only ones that you have to know. There are certain problems where knowing this might help you, and we're going to look at that in semester 2 in Calc 2. And even on this one, you could do that, but you do not have to know this. Okay, so fear not.